Hi guys, this is the EdExcel AS Level Further Maths paper from the June 2018 series, and in this video we will be taking a look at the FP1 option. Okay, so in terms of the examiner report overall for this paper, we've got a couple of points to make. This paper was accessible to many students. There were some testing questions involving coordinate geometry and inequalities that allowed the paper to discriminate well between the higher grades. In a significant number of cases, student solutions, and if you look at question 5 you can see what we mean, proved difficult to read. This was a result of either poor handwriting, incoherent working, or disorganized presentation. Okay, so for question number 1, we have to use the substitution t equals tan of x upon 2 to show that the equation 5 sin x plus 12 cos x equals 2 can be written in the form 7t squared minus 5t minus 5 equals 0. Now, the first thing that I would recommend that you do for part A of the question, I would suggest writing out sin x, cos x and tan x all in terms of t. You should be familiar with the results. Sin x, that's equal to 2t over 1 plus t squared. Let's just write this down. So we have 1 plus t squared. Cos x, that's equal to 1 minus t squared over 1 plus t squared, and tan x, that's equal to 2t over 1 minus t squared. Okay, so these here are results which you should be familiar with. Now, we've got this equation 5 sin x plus 12 cos x equals 2. Let's just write that down. We have 5 sin x plus 12 cos x equals 2. We will now replace the sin x with 2t over 1 plus t squared, and we will replace cos x with 1 minus t squared over 1 plus t squared. So we have 5 lots of this thing over here, 2t over 1 plus t squared, and then we add on 12 lots of 1 minus t squared over 1 plus t squared, and this of course is equal to 2. And we will now multiply both sides by 1 plus t squared. And so therefore we have 5 lots of 2t plus 12 lots of 1 minus t squared equals 2 lots of 1 plus t squared. Okay? And if we expand and simplify all this, on the left hand side we have 10t plus 12 minus 12t squared. On the right hand side we have 2 plus 2t squared. And therefore, in conclusion, we end up with 7t squared minus 5t minus 5 equals 0, which is the result we wanted to show. Now for part B, hence solve for x being in between minus 180 and 180, the equation 5 sin x plus 12 cos x equals 2, giving it answers to 1 decimal place. Now, from part A, we know that 5 sin x plus 12 cos x equals 2, in terms of t, is given by 7t squared minus 5t minus 5 equals 0. And if we solve for t, we can then use the substitution t equals tan of x upon 2 to find the values of x in this required range. And so therefore, solving this equation using part A of the question, if we attempt to solve this quadratic, we have t equals minus 5 plus minus 5 squared minus 4 lots of 7 lots of minus 5. Of course, this is square rooted, and then we divide the result by 2a. Okay, so we have 2 times by 7. And if we simplify all this, you'd find t is equal to 5 plus minus the square root of 165 over 14. Okay, and therefore we see that tan of x upon 2 is equal to 5 plus minus the square root of 165 over 14. Okay, so x upon 2, we can find out what this is, and what we see over here, this is nothing more complicated than regular A-level maths. Now, first of all, we need to make sure that we're in degrees, because remember, we need to solve x in between these values. So let's change the angle unit on my calculator quickly. And let's concentrate on 5 plus root 165 over 14. So we have the inverse tangent of 5 plus the square root of 165 over 14. You'd find this result to be 51.884. Now, does it make sense for us to add on 180? No, it doesn't, because you'll notice we'd have to multiply both sides by 2 to find x, and that will make x bigger than 180 once we multiply this by 2. So we can't do anything with that. So let's change this to a minus. We end up with a value of minus 29.265, etc. Okay, and now we need to ask ourselves, does it make sense for us to add and subtract 180? Well, no, it doesn't, because once we do that and then multiply by 2 to find x, the values of x we'll find would then be bigger than 180. So x upon 2 is equal to these two values, and therefore if we multiply both sides by 2, let's just write this down. So then if we multiply both sides by 2, you'd therefore find x is equal to minus 58.5 degrees, and we also have x equals 103.8 degrees, both to one decimal place. Okay? Of question 1, this was an accessible question with some students losing the final mark. For part A, we had to use the substitution t equals tan of x upon 2 to show that this equation here can be rewritten as this over here. This question was answered quite well, but there were some mistakes in the actual formula for sine and cosine involving t, but overall this question was well done. For part B of the question, where we had to solve this equation in this range, a lot of people solved the equation correctly by using part A to find a value of t. Now, once students got to this stage over here, there were some errors where students halved the values instead of multiplying by 2. There were also errors involving rounding to one decimal place as stated in the question, A couple of students found the value of t, as we have over here, and then substituted back into the formulas for sine and cosine to find out the values of x. Question number 2. The temperature, theta degrees C, of a coffee in a cup t minutes after the cup of coffee is put in a room is modelled by the differential equation d theta over dt equals minus k lots of theta minus 20, where k is a constant. The coffee has an initial temperature of 80 degrees C, and using k equals 0.1, we have to use for part A 2 iterations of the approximation formula dy over dx 0 equals y1 minus y0 over h to estimate the temperature of the coffee 3 minutes after it was put in the room. Okay, so the way I would approach this question for part A, now the coffee first of all has an initial temperature of 80 degrees C. That tells us that T0 is equal to 0 and theta 0 is equal to 80 degrees. And we're finding out after 2 iterations the value of the temperature of the coffee 3 minutes after it was put into the room. So after 2 iterations, T2, that's equal to 3, because we're considering the temperature 3 minutes after. And theta 2, well, that's what we're finding. Now, it takes 2 iterations for us to go from T0 equals 0 to T2 equals 3. And therefore, you'd notice here, H is equal to 1.5. Okay? Now, we know what d theta over dt is if we replace this k with 0.1. We say that d theta over dt, that's equal to minus 0.1 lots of theta minus 20. Okay? And we can use this approximation formula to write out an iterative formula. Of course, we don't have y and x, we have theta and t. So perhaps if we write this down in a different colour, we have d theta over dt naught. That is equal to approximately theta 1 minus theta 0 over h. Okay? And with this, we can write out an iterative formula. That's to say that theta of r plus 1 is approximately theta r plus h lots of d theta over dt r, where r is equal to 0, 1, 2, etc. Okay, so what we can now do is work out our approximation for theta 1 and then theta 2. First of all, we know that T0, theta 0, that's equal to 0, 80, and therefore we can use this information to find out the value of d theta over dt naught. Okay, and we can do that by substituting 80 in for theta over here in this differential equation. So we have d theta over dt naught that's equal to minus 0.1 lots of 80 minus 20, which is minus 6. And now that we know d theta over dt naught, we can use that to find out what theta 1 is. Theta 1, that's equal to, using this formula here, theta naught plus h, which is 1.5, lots of d theta over dt naught. So substituting in the values, we have 80 plus 1.5 lots of minus 6, and if you work this out, it turns out you get 71. Okay? And therefore, in conclusion, T1, theta 1 is equal to 1.5, 71. Remember, T1 is equal to 1.5 because we're going up in steps of 1.5. So we start off at 0, then we go to 1.5, and then we go to 3. And with this now, we can find out what d theta over dt naught is in the exact same way we did before, substituting into this equation. So we have d theta over dt 1, that's equal to minus 0.1 lots of 71 minus 20, and working this out we get minus 5.1. Okay, and now we can find out the value of theta 2. Theta 2, that's equal to theta 1 plus h lots of d theta over dt 1. So we have 71 plus 1.5 lots of minus 5.1, which is 63.35 degrees C. Okay, so don't forget to add your units. And that's what we're looking for over here then. That's our final answer. And then for part B, the coffee in a different cup, which also had an initial temperature of 80 degrees C, when it was put in the room, cools more slowly. Use this information to suggest for part B how the value of K would need to be changed in the model. We have the following reason. We would need to decrease K to become a smaller positive value. Remember, it cools more slowly. That's the key in this question. It cools more slowly. Okay. Question 2 was concerning iterations using solving differential equations using an iterative method. This was well answered, this question, with many scoring full marks in part A. A lot of people did apply this iterative formula over here, which I wrote in blue over here. But the only error that people seem to be making was the value of h. I always say, write out what you've been given and what you're finding first, and from that you can quite easily deduce the value of h. For part B, where we had to explain a certain concept, a lot of students demonstrated a very good understanding of the model by suggesting that k should be decreased to become a smaller positive value. Many students suggested that the value of k would need to be decreased, which was allowed as an acceptable suggestion. Incorrect suggestions included increase the value of k, k should become more negative, or k should satisfy being in between -1 and 0. Question number 3. We have to use algebra to find the values of x for which x over x squared minus 2x minus 3 is less than or equal to 1 over x plus 3. So the first thing we can do is factorize this quadratic here on the left hand side. So we have x over x minus 3 lots of x plus 1 being less than or equal to 1 over x plus 3. And if we take everything over to one side, we have x over x minus 3 lots of x plus 1 minus 1 over x plus 3 being less than or equal to 0. Okay? And if we write these fractions over a common denominator, the common denominator would be x minus 3 lots of x plus 1 lots of x plus 3. Here, this term is the same as x lots of x plus 3 over x minus 3 lots of x plus 1 lots of x plus 3. Okay, the x plus 3's cancel on the top and the bottom to give the x over x minus 3 lots of x plus 1. And this term over here, this is the same as x minus 3 lots of x plus 1 over x minus 3 lots of x plus 1 lots of x plus 3. Okay, and this is less than or equal to 0. And if we combine these, now that we have a common denominator, and if we expand out on the top, we have x squared plus 3x minus, and if we expand and simplify here, we have x squared, then we have x minus 3x, which is minus 2x, and then we have minus 3. And on the bottom, we have x minus 3 lots of x plus 1 lots of x plus 3. And all this is less than or equal to 0. And on the top, if we tidy that up a little, hopefully you can see the x squared cancels, and therefore on the top we have 3x minus 2x, which is 5x, and then we have minus 3, which is plus 3. So on the top we have 5x plus 3 over x minus 3 lots of x plus 1 lots of x plus 3 being less than or equal to 0. And now we can sketch this. We have asymptotes at minus 3, minus 1 and 3, and we have an interception point on the x-axis at the point minus 3 over 5. Okay, so let's quickly sketch this. So we've got a graph like this. It crosses at minus 3 over 5, and we've got our asymptotes. We have a linear over a cubic, so we have this sort of graph. So when we come to find out the values which are less than or equal to 0, we're looking below the x-axis. You'd find over here in conclusion that the set of values we're after, we have minus 3, which is less than x, which is less than minus 1. Now you have to be a bit careful over here. It's not less than or equals to, because we have asymptotes here. Or we can have x belonging to a set of real numbers, x being in between minus 3 over 5. Notice the less than or equal sign because we're looking at where the graph is less than or equal to 0, below the x-axis. And then we have less than 3 because of this asymptote here. And that's our final answer. Question 3 was concerning inequalities. This question differentiated between students of all abilities. There were a variety of methods used. A lot of students used the method I did in the question by taking everything over to one side and then combining the fractions as we did over here, and those who did that got to this stage very well. Other students multiplied both sides of the printed inequality by x minus 3 squared lots of x plus 1 squared lots of x plus 3 squared, which is also fine. And those who did this made a number of algebraic and manipulation errors, although some manipulated the result to give a correct x minus 3 lots of x plus 1 lots of x plus 3 lots of 5x plus 3 being less than or equal to 0. In both of these methods, a significant number of students made bracketing errors by manipulating a correct factor of x lots of x plus 3 minus x minus 3 lots of x plus 1 to give an incorrect x plus 3 or an incorrect x minus 3. A few students obtained a correct quartic inequality, shown here, followed by a correct factorization of that. Most students understood the method of finding critical values and usually identified the correct regions. Many students who did not consider the validity of their answers at x equals 3, minus 1 and minus 3 wrote down an incorrect answer, and you can see those incorrect answers here. So I think what that's on about is using the fact that you've got asymptotes. Question number 4. A scientist is investigating the properties of a crystal. The crystal is modelled as a tetrahedron whose vertices are A with coordinates 12, 4, minus 1, B with coordinates 10, 15, minus 3, C with coordinates 5, 8, 5, and D with coordinates 2, 2, minus 6, where the length of unit is the millimetre. The mass of the crystal is 0.5 grams. For part A, we have to show that to one decimal place. The area of the triangular face ABC is 52.2 millimeters squared. So the first thing we can do is actually sketch out this tetrahedron, which I will do quickly right now. So having drawn the tetrahedron, we need to work out the area of the triangle ABC, and to do that we first of all need to work out the vector AB and the vector AC before we can work out the area of the triangle. And I notice in part B we have to find the density, and we're given the mass, so at some point we'd have to work the volume. In that case, it would also be a good idea to work out the vector AD. So first of all, the vector AB, that's equal to 10 minus 12, which is minus 2. So we have minus 2i. 15 minus 4, that's 11. So we have 11j. Minus 3 minus minus 1, that's minus 2. So we have minus 2k. The vector AC, 5 minus 12, that's minus 7. So we have minus 7i. 8 minus 4, that's 4. So we have 4j. And then 5 minus minus 1, that's 6. So we have 6k. And in terms of AD, that's equal to 2 minus 12, which is minus 10. So we have minus 10i. 2 minus 4, which is minus 2. So we have minus 2j. Minus 6 minus minus 1, which is minus 5k. Okay, so having worked out those vectors, for part A, the area of ABC, that's equal to 1/2 multiplied by the magnitude of AB multiplied by AC. So we have 1/2 times by the magnitude of AB, so we have minus 2i plus 11j minus 2k multiplied by AC, so we have minus 7i plus 4j plus 6k. Okay, and if we multiply those together on your calculator, we can do this quickly. Defining vector A, we have minus 2, 11, minus 2. Defining vector B, we have minus 7, 4, 6. So multiplying those together, we have vector A multiplied by vector B. It turns out we get 74i plus 26j plus 69k. So we have 1/2 multiplied by 74 squared plus 26 squared plus 69 squared, and then square root this. Okay, so we have 74 squared plus 26 squared plus 69 squared, then square root this, and then divide this by 2. It turns out we get 52.232, etc. to one decimal place indeed. We have 52.2 millimeters squared. And now for part B, we have to find the density of the crystal, giving your answer in centimeters cubed. So you have to be a bit careful here. We have millimeters and then centimeters here. We'll convert the units at the end. So first of all, you need to recognize that the volume of the tetrahedron, that's equal to 1/6 times by the magnitude of AD dot product with the product of AB multiplied by AC. Okay, so we have 1/6 lots of the magnitude of AD we worked out to be minus 10i minus 2j minus 5k, and we will dot product this with the product of AB multiplied by AC, which we worked out over here. We found that was 74i plus 26j plus 69k. So we will dot product this with this result over here, 74i plus 26j plus 69k. And continuing with this calculation, we have 1/6 times by the magnitude of the dot product of these two, 10 times by minus 10 times by 74, that's minus 740, minus 2 times by 26, that's minus 52, minus 5 times by 69, that's 345. So we have 1/6 multiplied by, well, here we have minus 740, minus 52, minus 345, that's minus 1137, and if we divide this by 6 and take the absolute value of that, it turns out that the volume is equal to 189.5 millimeters cubed. And to convert this into centimeters cubed, we'd have to divide this result by 10 cubed. So we get a value of 0.1895 centimeters cubed. And the relationship between the density, mass and the volume, density is equal to mass over volume. So density, that's equal to the mass over the volume. So we have the mass, which is 0.5, the volume, which is 0.1895. Okay, so let's just move this here. So we have 0.5 divided by this. It turns out we get 2.638, etc. So therefore, can't remember what was the accuracy. We'll give it to one decimal place. We have 2.6 grams per centimeters cubed to one decimal place. Okay. Question 4 was concerning the area of a triangle using vectors and the area of the volume of a tetrahedron using vectors. Most students, well, what this question showed was that there were a few students who had not revised the vector cross product formula, and even then you can do it on your calculator, so please do bear that in mind. Most students arrived at the given answer in part A by applying the method 1/2 times by the magnitude of AB times AC. Some students found the correct answer by applying the vector cross product between other two edges of triangle ABC, so for example BA and BC. A few students arrived at the given answer by applying the formula 1/2 times by the magnitude of AB times by the magnitude of AC times by the sine of BAC, where the angle BAC had been found by using the scalar product formula. In part B, where we had to find the density, many students applied the correct method, so we have 1/6 lots of AD dot product with the product of AB times AC and then take the magnitude of that to find the volume of the crystal. There were several manipulation and calculation errors seen in the evaluating the volume, with some students evaluating AB times AC to give an incorrect 74I minus 26J plus 69K. But yeah, you can see my solution on how we worked through that. And the final thing to mention is that many students converted the units correctly to find the density, with a few students converting the length to centimeters before evaluating the volume. The formula for density was known by most students, but there were instances where of density written as volume over mass, mass times by volume, or mass plus volume. This formula is nothing more than you'll meet at GCSEs, so please do be careful. Question number 5. The rectangular hyperbola H has equation xy equals c squared, where c is a non-zero constant. The point P with coordinates CP and c over P, where P doesn't equal 0, lies on H. We have to use calculus to show that an equation of the normal to H at P is P cubed x minus Py plus c lots of 1 minus P to the 4 equals 0. Well, first of all, with this equation here, we can rearrange that equation as follows. So far we have xy equals c squared, which if we rearrange that equation, you'd find y to equal c squared over x. And I will call this equation 1, we might need it later on. Now, this equation over here, we can rewrite this as c squared to the power of x minus 1. The reason I want to write it in this form is because I want to differentiate this equation so I can find out what the normal is at P. So, differentiating dy over dx, you'd find that to be minus c squared times by x to the minus 2, which if you want, you can write as minus c squared over x squared. Okay? So that's what dy over dx is, okay? So we have dy over dx equaling this. Now at the point P, we can find out the value of the gradient of the tangent. So at this point P, with coordinates CP and C over P, let's find out what dy over dx is. Dy over dx, you'd find this to equal minus c squared over CP squared. So we have minus C squared over C squared P squared, and happily for us, you'd notice the C squareds cancel on the top and bottom. We're left with minus 1 over P squared. Okay, and therefore the gradient of the tangent, that would be minus 1 over P squared, and therefore the gradient of the normal, that's minus 1 over the gradient of the tangent. So we have minus 1 over minus 1 over P squared, which is simply P squared. And therefore, using y minus y1 equals m lots of x minus x1, we can say that y minus c over p is equal to p squared lots of x minus cp. Okay? And if we multiply through by p, so let's just write this down. If we multiply through by p, then we have py minus c equals p cubed lots of x minus cp. And if we expand this out, we have py minus c equals p cubed x minus cp to the 4. And if I take everything over to one side and then factorize, first of all we have p cubed x minus cp to the 4, and then we have minus py plus c equals 0. And you'd notice we can factorize out a c from this term and this term to give us this result over here. You'd find we have p cubed x minus py plus c lots of 1 minus p to the power of 4 equals 0. We'll call this equation 2. And that's what we wanted to show. And now for part B, the normal to h at the point P meets h again at the point Q. We have to find the coordinates of the midpoint of PQ in terms of C and P, simplifying your answer where possible. So what we now need to do is solve equation 1 over here with equation 2 over here simultaneously. And we can do that by substituting in equation 1 into equation 2. So we have p cubed x minus py, so we have p lots of c squared over x. So we have pc squared over x. And then we add on c lots of 1 minus p to the power of 4. And all this is equal to 0. And if we multiply through by x, so let's just write this down. If we multiply through by x, you'd find we have p cubed x squared minus p c squared plus c lots of 1 minus p to the 4 x equals 0. Okay? And we can write this as a typical quadratic. We have x squared, an x and a constant. We can write an equation as follows. We have p cubed x squared plus c lots of 1 minus p to the power of 4 multiplied by x minus pc squared equals 0. And if you look at the coordinates of p, we see over here cp is an x coordinate of p, and therefore we can see that if I call this equation 3, we can hopefully recognize that x equals CP is a solution to 3. And the reason that's the case is, if you think about it, the normal to H intersects H twice, once at P and once at Q. And we already know the coordinates of P, and therefore we know one of the x coordinates of the intersection point, that's CP. And if x is equal to CP is a solution to equation 3, we can therefore conclude that x minus CP is a factor of equation 3. So what does this mean? Well, with this, we can now write this quadratic equation as the product of two brackets. So we have x minus CP, lots of another linear factor ax plus b. This is of course equivalent to p cubed x squared plus c lots of 1 minus p to the 4 minus p c squared equals 0. And we can now find the values of a and b by comparing coefficients. So let's just write this down. Now compare coefficients. And if we do that, if we compare the x squared terms, on the left hand side we have x lots of ax of them. So we have a as our coefficient of x squared, and on the other side we have p cubed x squared. So we see that a is equal to p cubed. And if we now compare the number terms, on the left hand side we have minus CP multiplied by b. So we have minus BCP, and this is equal to what we have over here. Sorry, here we have an x. Let's write it out neatly. So here we have x, and then we had minus c squared p equals 0. So that was my mistake. So what was I saying? Here we have a number term. Okay, we have minus c squared p. So we have minus c squared p, and therefore hopefully you can see b is equal to c. Okay, and therefore we can conclude that we have x minus cp lots of ax plus b. So we have ax, so we have p cubed x plus c, and this over here is equivalent to p cubed x squared plus c lots of 1 minus p to the power of 4 lots of x minus c squared p. Okay, and because we're looking at where this equation equals 0, we can therefore see that we have x minus cp lots of p cubed x plus c equals 0, solving x is equal to cp, or x is equal to minus c over p cubed. Okay, and here x equals cp is one of the solutions we've already met, and therefore the coordinates of q we can find by substituting this solution over here, we'll call this 4, into equation number 1, and that will tell us what y is. So we will now substitute in equation 4 into equation 1, and if we do that, we have y equals c squared over x. So we have y equals c squared over x, which we just found to be minus c over p cubed. And if we work this out, hopefully you'll find we have minus c p cubed. And therefore, the coordinates of q, we have the coordinates of q being minus c over p cubed minus c p cubed. And we want to find out the midpoint of pq. So therefore, the midpoint would be the midpoint would be 1/2 lots of the sum of the x's. So we have cp minus c over p cubed, and then we have 1/2 lots of the sum of the y coordinates. So we have c over p minus c p cubed. Okay, so what we have over here then is our midpoint. Okay. Question 5 was concerning conics. This question discriminated well between a lot of students. There were a significant minority of students who made no attempt or no credible attempt in this question. It was clear that some of these students had not revised this area of the specification, and I don't think this question was that particularly hard. It's nothing more difficult than you'd find at GCSEs, in your regular A-level maths. So to begin with, students used a variety of methods to find dy over dx, because we want to find the normal. So one of the ways you could do that was to rearrange for y and then differentiate. That was probably the easiest way. There were other methods, such as using implicit differentiation, or the chain rule with parametric equations. Some students used the coordinates of p to obtain an expression for dy over dx in terms of p, which was followed by a correct method for finding the gradient of the normal in terms of p. Many students who progressed this far usually applied the correct straight line method and achieved the given equation. A few students who didn't squared lost marks in part A, and I think it was quite obvious that you had to use calculus. It said use calculus. Part B, where we had to find the midpoint of PQ. First of all, you had to recognise that you're solving a simultaneous equation, and a lot of people did notice that. They substituted correctly y equals c squared over x, or x equals c squared over y into the equation given over here, which was good. And then eventually you'd arrive at some sort of a quadratic as shown over here. But at this point students struggled, and one of the reasons they struggled is because they attempted to solve this using the quadratic formula. I attempted that at first, but then I thought it would be too complex to try that. But I think if you notice that x equals cp is a solution, you can see that x minus cp is a factor, and therefore you can compare coefficients to find this other bracket that you needed. So that's what's said over here. Many students formed a 3-term quadratic equation, with some students at this stage unable to make any further progress. Of those who attempted to solve the quadratic equation, most used the quadratic formula. In many cases, the algebra became cumbersome and many students made algebraic errors, which resulted in their being unable to find either the x or y coordinate of q. Those who found the coordinates of q usually proceeded to find a correct method for finding the coordinates of the midpoint of q. So I think the real issue over here was actually finding the other coordinate of x and y. But I think if you actually use the method I say, or really practice on your algebra to use the quadratic formula, then if you practice on your methods, then you can quite easily arrive at the correct answer.